Hello. First of all, thanks for all the great questions in class today. I think one question that came up often was people were unclear on exactly what does the workflow actually look like when you go from start to finish on a crystal structure, like in the problem set. So I'd like to go through an example. I have another uh, X-ray data set here. It was collected for this molecule, which is a 2-chromanone derivative. So I'm going to start by navigating to my X-ray data folder. I'm in my home folder right now, and I'm going to cd change directory into X-ray data. I don't remember, so I'm going to list this directory. I'm going to change into week 1 extra practice. Okay. I have my ins file and my HKL file here, so we'll take a look at the ins file quickly. It should look pretty familiar. Okay, here we are with the symmetry instructions that determine the space group, the SFAC instructions, scattering factors for carbon, hydrogen, oxygen. We have the number of those atoms in the unit cell, and we have a TREF instruction which tells ShellXS to use direct methods. So make this a little bigger so you can read, and we'll switch over to the terminal and solve it with ShellXS, or at least we'll attempt it. So we could try to read this in terminal output, but instead I'm just going to look at it in OLEX and see if it looks right. So I'm opening the res file, which is the output of all the ShellX programs. Okay, so how are we doing here? Let's pull up a picture of the molecule that we're actually looking for. So, does it look right? Let's see. It looks like we have a couple of rings, so that's a good sign. I can see this oxygen atom sticking down over here. I can see an ethyl group. I can see the O ethyl. So this does look right, even though it has a few extra peaks that don't belong here. I'm going to make our job easier by going through and deleting those extra peaks right away. So I'm selecting these, and then on my Mac I'm going to press function delete to get rid of them. And now we have only the molecules that belong here. The atoms, excuse me. So the next step, as we discussed, we're gonna come back over to our terminal. First, we're gonna back up the inst file that we just made. So we'll use our backup script. Back up the inst file. We'll give it a little note here. If you haven't seen the way this works, we'll take a look at the backed up file here. The note goes at the top. It has a space in front, and that means that the ShellX programs are going to ignore it, but it's there if we need a reminder of what we were doing when we made this file. So we don't need this. I'm going to close it for now. I'll switch back to my terminal, take the res file that was output by ShellXS, and copy it over to the inst file so that we can reuse it. And now this old inst file is no good anymore. We need to open the new one. Let's make this big enough to read. Okay. So what are we looking at here? There was no heavy atom in this structure, so that means we only have Q peaks. The ShellXS didn't attempt to assign any atoms in this structure. So we're going to have to take these Q peaks and sort them out and figure out what atom is what. I'm going to show two different methods to do this. First, I'm going to go through the method that I wrote about in the handout, which is pulling the coordinates from OLEX2 and typing them directly in. Before we start naming atoms, we need a numbering scheme. So I'm going to go back to ChemDraw because I conveniently made a numbering scheme already. These numbers are based on the branching of the structure. I went around the main rings of the structure and named everything in order. Started with the oxygen that was sticking out, and I went 1, 2, 3 through 11 over at the other end of this ring. And then starting from carbon 3, I branched off carbons 31 and 32. And starting from carbon 4, I branched off atoms 41 through 43. So that's the numbering scheme we're going to choose, and you can see how this drawing lines up with the proposed solution from Shell XS. So now we have this. I'm going to move it down to the corner so we can still see the numbers. And I'm going to go back to text edit and start typing in atoms. And I'm going to start with O1, obviously. So I'm going to type this all in by hand. O1, we want to make this an oxygen atom, so that means we're going to look at the SFAC line. Oxygen is the third one, so the SFAC number is 3. I'm going to go down here, pull up the coordinates. Wake up OLEX so that I can see the coordinates. I'm going to type these in. Now I'll just start going around the ring, and then I'll go down the branches. Here's another oxygen atom, so we're going to remember to number it with SFAC number 3 instead of 1. This is O7. We're going to go up and continue with the second ring. This is C8. Atom type number is 1. I want to make sure I got that right. Okay, we're good. I'm leaving off the site occupancy factors and the atomic displacement parameters on these atoms because Shell XL is just going to fill in a reasonable default value for those when we run the first refinement. So we don't need to worry about that. Excuse me. We finished the ring, so now we're going to go over to the branched atoms, and we're going to continue going in number order. So I'm going to go to carbon 31 now. Now over to oxygen 41. Okay, that's all the atoms. Now we have all these Q peaks, and if we leave them in here, Shell Excel is going to try to interpret those as atoms too, so we need to get them out of here. We might want them later, so instead of deleting them, I'm going to take the HKLF and end instructions. I'm going to move them up. Shell Excel is going to stop reading as soon as it hits this point, so that means we can leave these down here safely and they'll just be ignored. I'm going to save this ints file. I'm going to come back and run Shell Excel. So let's look at the output here. R1 is 8%, and that's pretty reasonable for a halfway finished structure. The biggest difference features are plus 0.62 and minus 0.31, so that's about in the range that we would expect, but we're probably going to be able to judge this the best just by looking at the results in OLEX 2. So we're going to open the res file, which is the output of Shell Excel. Okay, so how did this turn out? It looks fantastic. The atomic displacement parameters, which are represented by the size of each atom, they all look reasonable. Everything is pretty consistent with each other. We can see in the difference map that now most of the biggest difference features represent hydrogen atoms. We have these 4 over here on the sp2 carbons. We have a couple hydrogens on the methylene here. We can see all 3 hydrogens for this methyl and the same for this other ethyl group over here. So everything is looking great here, and it's probably a good time to start adding in our hydrogen atoms. So we can continue working with the same ints file. We just need to get a picture of our molecule back so we know which atoms to apply hfix instructions to. Hfix has to go in front of the first atom in the structure, so I'm going to come up here. There's a few different types of CH bonds in this structure, so I'm not going to spend too much time explaining the types of hfix instructions, but we can use hfix 4,3 for a planar aromatic CH like we used in the first practice structure, and that's going to be carbons 8 through 11. Do that first. Hfix 4,3 C8 through C11. Hfix 2,3 is for a CH2 group, so 2,3, excuse me. That's going to be C31 and C42. And then finally, a freely rotating methyl group is Hfix 137, which we already covered, and that's carbons 32 and 43. Oh, I'm missing a couple. Well, you know what? Let's run this refinement and see what it looks like, and then we'll find the ones that we missed. So I'm going to save this file. I'm going to go back to my terminal and run Shell Excel again. And just press up twice to bring back the old instruction. So the R factors improved a lot when we added those hydrogen atoms. They went from 8% to less than 6%. We still have the same size difference features, but we'll see what's the reason for that. And pull this up in OLEX again. And we can see by the 2 darkest gold peaks that we're missing 2 hydrogen atoms. They're both on sp3 carbons that are attached to 3 other carbon atoms. So we're going to use the hfix code 13 for that. We'll fill this in. We're still working with the same ints file. Hfix 13. What are these atoms? I'm just going to use OLEX to pull up their names. This is C3. And the other one is right next to it, is C4. Okay, save this again, go over and refine again. Now the R1 is at 5%, and the difference features are a lot smaller because we took care of those last two missing hydrogen atoms. So there's just a couple more important things to do here. First, we're going to make the refinement anisotropic for all non-hydrogen atoms. We do that simply by typing anice at the top of the file. We can put it after the hfixes. Save this again and run it. Now R1 is at 3%, and the difference map is even flatter, less than 0.2 electrons plus or minus. So that's great. We shouldn't forget to put in a temperature instruction so we can represent those hydrogens more accurately, and at the same time we'll put in a few other instructions like I discussed in the handout. So this was measured at 100, so the temp 100 Kelvin or minus 173 Celsius. We're going to change bond to bond $H so that we cover the hydrogen atoms. We're going to put in conf for torsional angles. I'm going to put in acta to output a CIF file. Save this again since the temperature is going to change the model a little. I'll run this refinement. Okay, so we'll take one more look in OLEX, but I'm expecting that everything is going to look pretty good. These difference features, they're all small now. If it's good, you'll see them in random places. If it's really excellent, you'll see them on the middle of carbon-carbon bonds because the electron density is deformed by those bonds, and that deformation isn't covered by a basic independent atom, the X-ray scattering model. So the fact that we're seeing a lot of difference features on carbon-carbon bonds is a sign that this refinement worked really well. The last thing we need to do is fix the weighting scheme for this refinement just a bit. So we're going to do that by opening the res file in TextEdit. We're going to scroll down to the bottom of this file. After the word end, we have a line with a suggested weighting scheme. I'm going to copy this line, come back to the inst file, and put it at the top. We can put it right after the other refinement instructions. Okay, let's save this from the refinement. I'm going to notice that right now the weighted R2 factor is 10.1% and R1 is 3.1%. So let's run the refinement and see how those change. Okay, we changed the weighting scheme. The weighted R2 dropped by a couple percent, and R1 was basically unaffected. So you can see the logic in that. This one is accounting for the weighting, and so it's affected by the weighting scheme. It takes a minute for the weighting scheme to converge, so we're going to go back and forth a couple more times and copy the suggested weights back into the inst file until they stop changing. So we're going from 436 and 17 to 372 and 23. So that's a pretty big change. It means we should probably do it a couple more times. I'm going to save this, refine again. Now I need to come over and close the previous res file. That's one of the fun things about TextEdit. We'll open it again, scroll down. This is a repetitive process. Copy this weight line. Remember to close this time. And come back to our inst file, same one we've been using all along, and paste this in again. That was a smaller change in the suggested weighting parameters, so that means we're getting there. Run the refinement again. Open the res file. Scroll down. Copy the suggested weights. close the res, go back to the ints, paste the suggested weights in, and now we can see that they've hardly changed at all. So we're going to be finished after this round. I'm going to save this, come over, run shell XL one more time, and now we can see that the difference map is even flatter than it was before, with the pluses and minuses about equal to each other. R1 is 3.1%, so we're going to scroll up and compare that to RInt and R sigma. RInt is 1.7%. That shows that the crystal is really good quality. R sigma is 2.7%, 3.1%. They're close enough to each other, and we can see based on the other features of this refinement that we're doing fine here, and we have nothing major left to worry about. There is one sign of concern for us here, which is the shift over ESD statistic for this refinement hasn't quite converged to 0 yet. We're still looking at 0.6 maximum, which is too big, so that means we should do a few more refinement cycles. We'll come over, find LS4, and change this to 20, just to be safe. I'm going to save this, run the refinement again. Okay, now the refinement is fully converged. Everything is exactly where it wants to be. The R factors are still good. Unfortunately, we might need to go back and double check the weighting scheme here, so I'll open the res file one more time. And we'll see how these compare. Scroll to the bottom for the suggested weights. These are suggested at 0356 and 2463. And you know what? That is close enough to the weights that we're already using, so we're not going to worry about it. So we'll take one more look in OLEX. But we can already see that the difference map is as we discussed, and all the atoms look reasonable with their ADPs consistent with each other, and generally consistent with the way that you would expect atoms to vibrate in a crystal. So we're finished here. We're looking good, and later on in the course we'll discuss how to turn this into a publication quality CIF file. So there's one other thing we should discuss, which is, and if you're satisfied with this, feel free to stop watching the video at this point. But there's a second technique for turning Q-peaks into atoms in the structure. And if the process that we used seemed a little, I don't know, clunky to you, then we can talk about this alternative. So we're going to start pursuing this other path by going all the way back. Let's see. We'll pull up the backed up ints file that we made at the beginning, and we'll start from scratch here. We might as well back up this finished one that we just made before we do that. So I'm going to back up our ints file. I'm just going to call this all finished. And I'm going to copy the original one. What is this? The first one is from 1831. We're going to copy this over to week1.3.ints. Okay, we can run shell XS on this again, and we'll be right back where we started. So here's the density map that we saw once already, and I'm going to clean it up same as before by deleting some atoms here. Now, let's clean up our workspace a little too. We'll get rid of this stuff that we added to the inst file. The temperature and weighting scheme, we added those, so we'll delete them. hfix instructions, all these atoms. And now we just have these QPeaks with coordinates. So instead of using OLEX to get the coordinates, we're just going to use OLEX to get the names of the QPeaks that we want to turn into atoms. And we'll do that in the order that we selected in our weighting scheme. So we'll put this here so we can refer back to it. And we're just going to go through this structure in numerical order and find the appropriate QPeaks to turn into these atoms. So starting with O1, we're going to come over here and see what its name is. This is Q3. So I'm going to take Q3, I'm going to cut it, bring it up here, rename it as O1, and set the scattering factor type correctly. There's an extra number at the end of this line, which is the intensity of the density feature for this atom, but it's just going to get ignored by ShellXL, so I'm going to ignore it too. I'm going to keep going. Continue with C2, which corresponds to Q4. Bring this up here. Keep going around the ring. C3 is Q14. C4 is Q13. C5 is Q8. I'm cutting these lines instead of copying them because it makes it easier to see the ones that you haven't used yet. C6 is Q11. O7, that's Q1. That makes sense because oxygen is the strongest scatterer. And we'll change the scattering factor type. Continuing with C8, that's Q5. I'm triple clicking on these lines to select the whole line at once. C9 is Q7. C10, Q10. C11 is Q9. Now we go to C31, which is Q6. C32 is Q16. O41 is Q2. C42 is Q15. And C43 is Q12. So it's nice to see that the strongest 16 density features in the proposed solution all corresponded to the 16 real atoms in the structure. And this other weaker stuff, we were right to ignore it. So now we've we've built up this structure exactly the same as we did before. We just did it by a different technique. So I'm going to hit save on this. Oh boy. It's unhappy because we changed the file in the terminal when we copied our backup copy over to the original name of the inst file. We know what we did, and we know that this is the way we want the file to look, so we can just go ahead and save anyway. Let's see how this looks after we refine it. Illegal parameter, what does that mean? Let's open the list file and see what it's unhappy about. Oh, okay. We have bond and fmap on the same line. I shouldn't be so I shouldn't be mysterious. I looked at the last line before we got the illegal parameter in our list file. ls is the last line that's okay, so I went down to the first line that's not okay, and it was bond and fmap together. So that's how I knew to check that. We'll save this, go over, try the refinement. What's illegal now? Open the list file again. Oh, sorry, I'm running the wrong program here. I need to run shell XL. Okay, now we're good. And we've gotten to an R1 of 8%, just like we did the last time that we assigned all the atoms and didn't do anything else. So let's take a look, make sure everything is the same. And yeah, all the atoms we put in look pretty happy, and we can see that the hydrogen atoms belong here now. So we won't go through the same process a second time, but you can see that there are two ways to get all your heavy atoms in. And once you do that, you're going to go ahead and add your hydrogen atoms and make everything anisotropic and go through your cleanup items. So I hope this demystifies the workflow a little, and I will look forward to discussing it more next week. Thank you.